Hi, welcome to Module 6. Module 6 is on functions. We'll talk about what a function is and how to identify it. We're also going to get into domain and range, and then we're going to follow that up with learning about specific types of functions like linear functions, quadratic, exponential functions. There's a lot packed into this module. You could spend, several months in an algebra course talking about all of this, and we're going to really just touch on the important parts all in one module. So it's important to just kind of understand that we're just looking at this from a bird's eye view. It's not, you don't have to know every specific thing about each of these types of functions. Really just kind of make it a goal to understand like the basic overview of all of this. And I'll show you some tricks along the way that'll help with that. So one of those tricks is to use a graphing calculator. And I know we said at the beginning of the course you don't need one, and you don't need to buy one, but there's a really nice one online, and I want to show you what it is. It's called Desmos. So if you just Google Desmos, you'll see this pop up, and all you have to do is click on graphing calculator, and you will see the graphing calculator. Let me make this a little smaller so it fits in the screen. There we go. And basically all you have to do is type in this box what you want it to graph, and it will come up for you. And if there's ever any specific symbols you need, then you can just click on this calculator or this keyboard icon at the bottom, and then you've got some options there. So we're going to use that in this lesson. So that's something if you want to pull up right now as you're watching the video, and that way you can try it yourself when I go through it. So I'm going to put that away right now. We're going to start and just talk about what a function is. So we start by defining what a relation is actually, and that's what goes in this first blank. So a relation, and we need this term because it helps us define function. A relation is just a rule, okay, matching up two sets of objects. So we talked about sets before in previous modules. So sets we usually denote with curly brackets. So you can see here are some sets here. We use curly brackets. This first example, we've got this rule, and it matches the company with its stock abbreviation. So Apple has the abbreviation AAPL if you look at the stock market. Ford, the company Ford, has the abbreviation F. Google, GOOG, and so forth. And then we've got this second example here. This rule is not so obvious, but we've got two sets of objects that are matched up. In this case, they're numbers. So the 9 is our input. We could consider that X. 0 is our Y value or our output. So the input is linked with an output. The input X is linked to an output. And a function is a specific type of relation. So a function is when you have a set of ordered pairs, kind of like set B here, but where no two ordered pairs have the same first coordinate and different second coordinate. So for example, if we come up here and we look at this one, so this example right here, 3, 9 and 3, 3. The X coordinate 3 goes with 9, which is a Y coordinate, and the X coordinate 3 here goes with 3, a different number. And so because we have one X going to different Y's, we would say this is not a function. So not a function because the X, which is 3, is paired with two different Y values. Okay, and then visually, if you're a visual learner, one thing you could do is you could plot these points. So if you plot all of the ordered pairs, if you ever see ordered pairs that are stacked on top of each other vertically, that's a visual way to show that it's not a function. So in this case, we would have 3, and then 1, 2, 3. I'll try to make it small so I can fit in 9, 4, 5, 6, 7, 8, 9. And so we've got 3, 3 plotted, and then 3, 9. And there's something called the vertical line test. And if you're a visual learner, this might be what you want to use to determine if something is a function rather than just looking at it in a list. So vertical line test just basically says you should be able to draw a vertical line anywhere on the graph, anywhere on the picture, and it should never cross through more than once. That if we do that here, if we draw a vertical line, it crosses through 2 points, which violates that test. So that shows us visually that it's not a function. So, and remember, we've got that graphing software, Desmos. If you ever have an example on the homework or down below, I'll show you. If you have an equation rather than a list of ordered pairs, you could actually just graph it and then use that vertical line to test whether or not it's a function. So we kind of answered this a little bit, one of these questions. So which of the above examples of relations are functions and why? So we already said B is not a function. So I explain that right here. B is not a function. Let's look at A. So again, we look at all the X values. So Apple, Ford, Google, Kraft Foods. Are all of those X's going to one Y, meaning like, is Apple only associated with one abbreviation? You don't see Apple in the list, like you don't see Apple and then another abbreviation, like maybe AP or something. That would make it not a function. Since each of these X's go with only one Y, we say yes, it's a function. So A is a function because each X value is paired with only one Y value. Okay, so there's some practice below. This would be a great time to pause the video and try these on your own. So practice identifying functions. So which of these are functions? So the first one, this is a good one because if you notice all of the X's, you don't see any repetition with the X, but there's a bunch of repeats on the Y's. All of the Y values are the same. And this is a tricky one because sometimes it's easy to get these mixed up. It's okay for Y to repeat itself. You don't want X to repeat itself. What you wouldn't want is like, let's say square root of 3 comma 13, because that repetition with the X value would tell you that X square root of 3 goes with more than one Y, and that would violate that rule of something being a function. So I'm going to erase this because that was just an example. So in this case, I'm going to say yes, each X has only one Y value. Meaning 5 only goes with 10, 5 does not go with 15 or 30 or negative 2. And then in parentheses, I'm just going to put it's okay for Y to repeat, just not X. For the second one, so this is a little different. We don't have a list of ordered pairs. You could do a couple of things. You could think about it in terms of the equation, and you could think of this in terms of like a table of values. So you could make a table of values on the side and say, okay, well, how does this function work? Well, I could pick some X values, plug them in, and find Y. And then as I'm doing that, think, okay, if I plug an X in, is it ever possible to get more than one Y? So for example, if I put in 2, 2 squared is 4, so Y would be 4. Would it ever be possible to put in 2 for X and then get something else for Y? That doesn't seem possible to me, but you could try this a couple of times if you wanted to. Like maybe I tried negative 2. Well, negative 2 squared is positive 4. And so yes, I got the same Y, but remember in part A that happened and that was okay. It's okay to have Y repeat. You just don't want the X to repeat because then that tells you that it goes to more than one Y. And you could keep doing this. Another option at this point would be to pull up that Desmos and let's look at the graph. So I'm going to go ahead and I'm going to plug in Y equals, and then I'm going to plug in an X and then press this squared button. And so we see this function, it's a parabola, and I want you to imagine, I'm going to do it with my cursor. I'm going to just kind of bring my cursor down and imagine vertical lines being drawn through this picture, drawn through this graph a bunch of different times. Is it ever going to cross that red curve more than once? And the answer is no. So this visually proves that this is a function. So it looks like this, passes the vertical line test. So we say is a function. You could have also said, forget the vertical line test, you could have said, yes, it's a function because X will only be paired with one Y. Every X only goes with one Y. Next, we've got two other functions here, and you'll notice these are a little bit harder to make a table of values because the y is not being solved for. You could solve these for y and make a table of values. I'm going to just use the graphing software. And again, like I said in the beginning, like if you were spending an entire course on this, you would come at this from a variety of different ways and spend multiple days on each. But since we're just doing this in one module, I think let's just use the method that's most convenient. The cool thing about Desmos is that you can plug it in. This is not like a graphing calculator, a handheld one, where you have to solve for y. You can plug this in exactly how it's written with the x and the y. You don't have to do any work. Plug it in exactly how it looks on your page, and then you've got the picture. And so we've got another, this is called a parabola, only it's pointing downwards. And so if I take my cursor and I draw a bunch of vertical lines, and I ask myself, is it ever going to cross more than once? The answer is no, it's never going to cross more than once, so it must be a function. So I'm going to say for that one that it's a function, and I'm going to say passes vertical line test. Now keep in mind, if you ever had a parabola facing this way, then it would not pass the vertical line test, because when you drew a vertical line, it would cross here and it would cross here. It would cross twice. But whenever you have a parabola that's either just facing up or facing down, then those will always pass the vertical line test, because vertical lines will never cross more than once. So just something to think about. And then lastly, we've got this last function with an absolute value. So I'm going to pull up Desmos again, and I'm going to plug that one in. So this one, I'm just going to say x equals, whoops, not plus, x equals, and then I'm going to use the absolute value button down here, absolute value of a, and then I'm going to plug in y. And you can actually, it does the last line for you. So you've got this, it's a V-shaped graph, but it's sideways. So if I draw some vertical lines here, you can see that it crosses more than once. And for example, you could also look at this in terms of the points. So say, for instance, we look at this point right here. That would be 1, 1. There's a point down here that's 1, negative 1. And so if you wanted to make a list of the points that this red line goes through, both of these lines, you would see that looking at those points in a list that you'd have x's that go with more than one y. Or you could look here, 2, 2 is a point on the graph, or 2, negative 2. Well, you can't have 2 going to multiple y's, and so this is not going to be a function. So we're going to say no, not a function. And we could say does not pass the vertical line test. And then x, you could also say x values are paired with more than one y. For example, 1 went with 1 and 1 also went to negative 1, and that is not allowed if it's a function. Okay, so we're going to go to the next part now, and we're going to talk about function notation. This is something that you may have seen before, and I think it almost looks more confusing than it is. Function notation is when you see a function, instead of an equation like y equals x squared, if it's written f of x equals x squared, then this is called function notation. These mean the exact same thing. The reason that we use function notation is because it makes it really simple in terms of writing out problems and solutions, because we can actually show that we're plugging things in using this function notation. And we'll get to that in a minute. So the equation y equals x squared, it represents a function, and that's a function. It has a graph that looks like this, so it passes the vertical line test, so we know it's a function. We talked about that above. And it relates variables x and y. So we plug in an x and we get a y value out. So we call the x, which I often call input, but we call it the independent variable. And I'm just going to put in parentheses input. It's kind of like what we plug in. It's the number that you plug into the function. And then we call y the dependent variable. Because its value depends on the choice of x. And this is what we call the output, and it's the result that you get when you plug that x, the number in for x. Another way to write the same function is f of x equals x squared. So I wrote that down above. This is known as function notation. And we say this aloud as f of x. So whenever you see the parenthesis, that's just of. So f of x equals x squared. The independent variable is sometimes called the input. So I wrote that above. I can write it again. The dependent variable, y, is sometimes called the output. So let's try writing this equation in function notation. Now, one thing that you're going to want to do is you're always going to want to solve the equation for y, which just means get y by itself on one side. And that allows us to replace that with f of x. So we're going to take 3x minus 2y equals 6, and we're going to get this y by itself. So the first thing we're going to do is we're going to get rid of the other terms that are on this side. So 3x, we want to get rid of it. If you want to get rid of it, we're going to subtract 3x from both sides, because 3x minus 3x is just 0. So those go away. Don't want to forget this little minus here. That stays with the 2y, so negative 2y equals. These are not like terms, since one is an x and one's a number, so you're just going to write it 6 minus 3x, or you could write it negative 3x plus 6, either one. And then I'm going to come over here, and I'm just going to write that down again. And then I'm going to get rid of the negative 2. Right now, y is being multiplied by negative 2, so I'm going to do the opposite and divide by negative 2. And then you've got to make sure, this is tricky here, a lot of people make the mistake and they just divide one of these terms by negative 2. You have to do it to everything. You have to do it to the entire right side in order for this equation to still hold true and be balanced. So these negative 2's divide and become 1. So negative 2 divided by negative 2 is just 1. So 1y I can just write as y equals 6 divided by negative 2. So 6 divided by negative 2, a minus and a minus here turn out to be a plus. So we could write that as plus 3 halves, and then the x just comes along for the ride. You can stick the x with the 3 on top or just put it out front. And then I can simplify 6 over negative 2 by just writing the negative out front, and then 6 divided by 2 is 3. So y equals negative 3 plus 3 halves x. You could also write it, I'm just going to put or, y equals 3 halves x minus 3. Either is fine. It doesn't matter the order in which you write these terms. But then our last step, so step 2, is replace y with f of x. So where you see the y, we're just going to write f of x equals 3 halves x minus 3, and then we're going to circle this, and we are done. And that's how you change an equation into function notation. Okay, so we're going to move on to the next page. We're going to talk about evaluating a function. So evaluating just means to plug in. I often say plug and chug. It means just to plug whatever value you're asked for in for x and find y. And the shorthand notation for this is just f of whatever number they want you to plug in. So for instance, f of 3 means to take 3 and plug it in for x in the function f. So you'll notice there's f's here, and then there are also, you see g, that just tells you what function you're looking at. So there's this function f of x and then g of x. So if we want to find f of 3, it means take the function f of x, which is up here, and we're going to plug in 3. So I'm going to write in x squared plus 3x minus 5, and then I'm going to plug in 3 wherever I see an x. So 3 squared, and I always get in the habit of writing parentheses when you're plugging things in with a square, because it'll help you if you ever decide to use a calculator, you want to use parentheses. So plus 3 times 3 minus 5, and so 3 squared is 9, plus 9 minus 5, we end up getting 13. Okay, f of negative 2. And this would be a great place to pause the video and try the rest on your own and then double check. the answers when you're done. So this one's a little bit trickier because you're plugging in a negative. So we're dealing with the same function as above, so I'm just going to write that down. When you're plugging in a negative, make sure you use parentheses in your calculator. If you plug -2 squared with parentheses in the calculator, you're going to get 4. If you plug it in like this, you're going to get -4, and that'll cause you to get the wrong answer. -2 squared means -2 times -2, and so if you want your calculator to do it, then like that, then you have to put parentheses. Or you can just do it by hand, and then you avoid any potential mistakes with the calculator. And so if we evaluate this, -2 squared is 4, minus 3 times -2 is -6. So I'm going to write -6 and then -5. And then we get -7 altogether. And then not f, we're going to do g of 0 here. So I'm going to write down function g, 4 plus the square root of x plus 1, and I'm going to plug in 0 for x. So 4 plus the square root of 0 plus 1, which is 4 plus the square root of 1, and the square root of 1 is just 1. So 4 plus 1, I get 5. And then last, g of -3 is equal to 4 plus the square root of x plus 1. So you're going to plug in -3 plus 1. And so if we evaluate that further, we get 4 plus the square root. -3 plus 1 is -2. At this point, we have a problem. You can't take the square root of a negative number. So, and you could even double check this if you weren't sure with your calculator. Try negative or square root of -2, and your calculator will tell you it's undefined or there's an error. And so what you do in this case, if you ever have to evaluate something and it's not possible, then you're just going to say that the answer is undefined. And that'll be an option for you on Connect. So, and I'm just going to write a little note here. So can't have a negative sign under the square root. Okay, at least in the real number system, which is the number system we're dealing with here. So this next part, this can get a little tricky. We're going to domain and range. We're going to definitely rely on Desmos for this section because it'll make this a little bit easier. The domain, I'll start by explaining what they are. So the domain of a function is the set of all values of the independent variable x. So just remember, domain goes with x. So the set of all x values that result in a real number values for y. Basically what this means is all acceptable values of x that you can plug in. So all acceptable values of x that you can plug in. Sometimes, like we just saw in the example above, we weren't able to plug in -3. It resulted in a problem. So if I were going to talk about the domain for that, I would say x can't be -3. It doesn't work. The range of a function is the set of all possible y values. So what's possible to get out as an output after you put any x value that you're allowed to put in as an input. And so you can think about this in terms of an equation, like you can, for example, for a, let's talk about a. So f of x equals x squared. You could think about this in terms of this equation. So remember, f of x equals x squared is the same as y equals x squared. So if it's simpler to think of it that way, you can. You could think, okay, are there any x values that I cannot plug in there? Like, is there any number where I can't, where it's a problem to square that number? The answer is no. You can plug in any number you want because you're allowed to square anything. There's no restrictions on squaring number. So for the domain, we say x can be anything. And the math way to write this, and this is how you're going to have to write it in Connect, is that you can say that x can be all real numbers. And I'll show you, I'm going to pull up Connect real quick, and I'll show you what that's going to look like. So when you're doing a domain problem, the domain in set notation is, you can, if you want to, if the domain is all real numbers, which is basically just means any number, you can just click this R button. And that's a much easier way to enter that answer. and it was marked correct. And just to show you, it's a different equation than the one we're working on, but that's the example. The other way that you can write it, so let me go back to the notes. So you can say, so there's two options. You can say, one option would just be to say all real numbers, that's the quickest. Or the next option is you write it in set builder notation. So you write a curly bracket. Set builder notation in general has a curly bracket on each side. And then you're either going to put an X or a Y here, depending if it's domain or range, a vertical line, and then you're going to describe, so this is going to be a description of the domain or range. So in this case for domain, we're going to say all values of X such that X can be any number. And the way we write that is X can be greater than negative infinity, and negative infinity is an option in Connect. You can click on the button that shows the symbol, or it could be less than infinity. And this is just a way to describe that X can be anything. The range is, infinite. And so the range here, okay, remember range is Y values. So think about for all the values that you can plug in for X, you can plug in any number you want for X. You could plug in 100 or 1,000 or 1,000,000 or negative 1,000,000. Are there any Y values that you would never get as a result of putting in a number for X? One thing to think about here is your squaring. So if you plug in any number, even a negative number, you're never going to get a negative answer. So for example, if you plug in -2, you end up getting 4. If you plug in 2, you end up getting 4. Y is never going to be 0 in this case. And so the range, I'm just going to say Y will always be positive. So the way that we can write that is curly bracket, Y, all Y values such that Y is greater than equal to 0. And I put equal to 0 because it is possible to get 0 as an output. For example, if you plug in 0, so 0 squared, if X is 0, then you end up getting 0 for an output. Let me show you the picture. So if this sometimes can be confusing just thinking about it in this way, let's look at the picture. Let me grab, oh, we don't want Connect anymore. Let me see if I can find Desmos here. Okay, so I'm going to go back to Desmos and I'm going to plug in the function. So I'm going to go here and just X out the one we were just working on before, and I'm going to plug in Y equals X squared. If you look at this picture, so if you're looking at it in terms of domain, look at it from left to right, and as you move from left to right, are there any X values that are not going to have a coordinate with a point on the graph? So for instance, -10, there is a Y that's going to match with -10, and it's way up here at the top. You can't see it. Now you could zoom out, and as you zoom out, you can see that -10, which is right here, actually does hit the graph. So it's sometimes you need to zoom out to be able to see it, but it will match up with something. So there's never an X value moving from left to right that's not going to go and coordinate with something on the graph, a Y value. Now, if you're looking for the range, you want to look going top down. So we're going to go vertically and we're going to look and we're going to see if the Y value, so for instance, a Y value of 20, there's two Y values of 20 on the graph and they're right here. And I'm going to just think of this almost as drawing some horizontal lines. As I move down, I can see that all of these Y values are represented on the graph. Even 0 here, we've got 0, 0. But as I go into the negative Y values down here, notice there isn't a picture there. There's not a graph down there. And so this shows that Y is going to have to be greater than 0 because you see it starting here at 0, 0. So that just confirms what we just found. So the second one, f of x equals square root of x. So our domain, think of acceptable values for x. You cannot take a square root of a negative number. So that's something to think about. Anytime you have a square root in your problem, that's going to be an issue in terms of domain. It's going to affect your domain. So it is possible to take the square root of 0. So you're allowed to take the square root of 0. That's just 0, but you can't take the square root of a negative. So in this case, our domain is going to be curly brackets, all values of x, such that x has to be greater than or equal to 0. Whoops. Say, remind me tomorrow. There we go. I always get these reminders at the best times for the, and you know what, let's go to Desmos real quick and let's look at this picture. So square root of x, I'm going to erase this last one and I'm going to find the square root Oh, sorry about that. Likes to resize itself. I'm just trying to move this up so you can see I'm clicking. I know it's a little bit off the video, but I'm clicking on the keyboard here. And then there's a square root button. It's actually at the bottom right there. And that's what I'm going to click on. So I'm going to do square root of x, and there's our graph. So if we look going left to right, you can see that there are no negative x values that are represented on the graph. So the smallest one is 0, and then it increases from there. So x has to be greater than 0. Now let's look for y's. So as we go for y, we're going to look going down here vertically, moving up. So there aren't any y's down here. The graph is not located down where y is negative. So the biggest, or the smallest y rather, is also 0, similar to x. And then as we plug in bigger x's, y is also going to get bigger as well. So the range for this one is going to be y has to be greater than or equal to 0. So I'm going to write range all values of y such that y has to be greater than or equal to 0. And then this last one, so you can look at this one algebraically if you'd like, or we can look at the picture. One thing to think about when you have a rational function, which basically just means a fraction like this, you don't ever want the denominator to be 0. So denominator can't be 0 because you can't divide by a negative number, or I'm sorry, you can't divide by 0. And so one thing you can do algebraically is say, okay, well, I'm going to take x plus 1 and set it equal to 0 and figure out, well, what would x have to be in order to make that denominator 0? And if you solve this equation by subtracting 1 from both sides, you end up getting x equals -1. And so that tells you for the domain is going to be all values of x such that x cannot be -1. And then any other x value is going to be okay because you can divide by any number as long as you're not dividing by 0. And for the range, let's go ahead and look at the picture. It's a lot easier, I think, to look at a picture, especially with the range, but for both of them, actually, it's helpful. So I'm just going to plug in, I'm going to use parentheses, and I'm going to say 3x minus 2 and parentheses, and then use the division sign, which is just the forward slash. And as soon as I pressed the forward slash button on my keyboard, and it automatically made it into the fraction, which is kind of nice. And then at this point, you can just put x plus 1 at the bottom. You don't even need parentheses, but parentheses would be okay. And so you can see here for the domain. So x equals -1 is right here on the x-axis. And so you can see if you look up and down, the graph will never, you can even zoom out, the graph is never going to touch it. It looks like it does, but it doesn't. It's actually called a vertical asymptote. The graph gets really, really close to x equals -1, but it never touches it. Well, we're going to look for a similar thing with the y. So with the y value, I'm going to come up here. At this, it looks like there's a asymptote right here for y. Let me go ahead and zoom in a little bit more so we can see it a little bit better. You can see here, if we look at the graph, so for instance, like this point right here has a y value of 0. As we go up, the y is increasing, 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 increasing. It sort of flattens out. And if I'm going to zoom out a minute, or again, and it approaches this line, which is x equals 3. So 1, 2, 3. And if you look in this direction, that green line will never actually touch y equals 3. It gets very, very, very close, but it doesn't actually touch it. So that tells us that the range, let's write it down in our notes, our range is all values of y such that y cannot be -3. All other y's end up working. And so that would be the range for that one. Okay, so this next part, we're going to talk about linear functions. And linear functions are basically just straight lines. And it shows that in these bullets over here. So they're usually in the form y equals ax plus b, or you can think of it as mx plus b. So if you've taken an algebra class before, you probably learned about slope-intercept form, which is what this equation is written in. So this is called slope-intercept form. It doesn't have to be written in that form, but it's most commonly written in that form. When you graph linear equations, they make a straight line. And there's several different ways to graph these, okay? And I'm going to try to make this as simple as possible. Again, if you were taking an algebra class, you would spend probably several weeks talking about just graphing alone. And a lot of times when you graph in algebra classes, you talk about the slope, which is often known as rise over run, and then the y-intercept. And so it's possible to graph it that way. You can also make a table of values. So I'm going to show you both methods. And if one method just doesn't make sense, then don't even worry about it and use the other method. So I'm going to graph A using the slope in the y-intercept. So for function A, I'm just going to write it down here. Instead of f of x, I'm actually just going to write, well, I'll leave it f of x, that's fine. F of x equals 3x minus 2. The slope is always the number in front of x. So y equals mx plus b, or you could think of it like above, ax, plus b. The number in front of the x is always the slope, and the number by itself without the x is always the y-intercept. And so the slope in this one is 3, and the way we interpret that, if it's a whole number, I always like to put it over 1, and I like to think of it as rise over run. And if it's a positive rise, that means you're going up. If it's a negative number, it means you're going down. If the denominator is positive, it means you're moving to the right. If the denominator is negative, it means you're going to the left. And so this would basically mean up 3, right 1. So you start by, actually I got ahead of myself, that's the slope, but you need to actually start with the y-intercept, which is negative 2. So the y-intercept is negative 2. That means you locate the y-axis, you go down 2 on the y-axis, you plot a point, and then you take your slope, which is up 3, right 1, and you move from there. So your slope is like your direction. So 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1, and then you can connect the points. You can also go down 3 to the left 1, because that'd be negative 3 over negative 1, which reduces to 3 over 1. So, and then you're going to get a straight edge, which I don't have, so I'm going to do the best job I can. Bear with me, and then connect them and make a line. If you're graphing it and your points do not line up to make a line, that's a good indication that you did something wrong. So if the function only has one x, if it's a linear function, then you know it should be a straight line. So that's a good way to check your work. The second method, so I'm going to write down the next one. And the next one, instead of f of x, I'm going to write y equal 2/3 x plus 3. I'm choosing to write y because I think it makes it a little bit simpler in terms of doing a table of values as xy. So what you can do is you can make a table of values, and this will work for any function. And all you have to do is pick a couple of x values. So I might pick, and I'm literally just making these up. I am going to look at my graph though. I'm not going to pick numbers that are off the grid. So I'm not going to pick like negative 100. I always like picking x equals 0. And actually I shouldn't put that point on there because I don't know that's there, but x equals 0. And then maybe I'll pick negative 3 and 3, a negative and a positive. And then what you're going to do, oh, and I want to mention this, I picked 3 and negative 3 because I'm looking at this fraction and I know that it'll make the math easier when I evaluate this. So keep in mind, you get to pick the x's, pick something that's going to make it easier to evaluate. So I'm going to plug in negative 3. So I'm going to do 2/3 times negative 3 over 1. I can always put it over 1 plus 3. The 3's end up canceling. So they cross cancel. 2 times negative, this is actually like a 1 because 3 goes into 3 one time. So it's 2 times negative 1 is negative 2 plus 3, and I end up getting 1 as an output. So when I plug in -3, I get 1. And keep in mind, you can use your calculator to evaluate this. So if you're not strong with fractions, you can pick whatever number you want and just use your calculator. So the point -3, 1 is on the graph. So I'm going to go 1, 2, 3 to the left and +1. And then I'm going to plug my next value, 0. This one will be easier. 2/3 times 0 plus 3. Anything times 0 is 0, so that cancels out. So we just get 3. So 0, 1, 2, 3 is on the graph. And then last but not least, let me just scroll up a little bit so I have some more room. So I'm going to write 2/3 times 3 over 1. I'm plugging in 3 for x. These 3 cancel. So 2 times 1 is 2 plus 3, and I get 5. So 3, 5 is my other point. 1, 2, 3, 1, 2, 3, 4, 5. And you can see that they all line up. So that's a good indication that I did my math correctly. And I connect them with a straight edge, and I make my line. And I could have said, oh, the y-intercept is 3. The slope is 2/3, which means up 2, right 3, and that would have gotten me the graph too. So like I said before, pick which method you like and just don't worry about the other one. So the other part, we're not done with linear functions, so that's graphing, but we're also going to talk about interpreting the graph. So we're going to do some story problems with linear equations, and then we're going to talk about how to write a linear equation when given a scenario or a story problem. So this next part, interpreting the graph of a function. So this is a graph that represents the percentage of babies in the United States born to unwed mothers since the year 1970. Okay. If you look at the bottom, I don't see any years here that are written like 1970. So because it says since the year 1970, you can consider 1970 being 0. That's sort of like the starting place. So 1970 is right here. So at the bottom, the x-axis, this is what we're going to label years. And then on the y-axis, I'm going to label percentage. And you could even go as far as to write, instead of 10, just write a note. So 1970 plus 10 would be, so this would be equivalent to 1980. And then if we go another 10, which is 20, so 70 and 20 is 1990. So if you wanted to write it like this, another 10 more years, that would be the year 2000. And then we'd have 2010 and then 2020. So you could do it like that if you wanted to. And so question A says, about what percentage of babies born in 2005 had unwed mothers or unmarried mothers? So it's great that we wrote the years at the bottom, because now we know, okay, if 30 corresponds to 2000 and 40 corresponds to 2010, then in between, which would be 35, would correspond to 2005. So this is 2005. No, it's small. Hopefully you can see that. So what we do is we go up and we see, well, what y value does that correspond to on the graph? So then we kind of look, and it's helpful if you use a straight edge here, even like, you know, a driver's license is helpful. And then you look and see, well, what y value does it correspond to? To me, it looks like maybe, I'm going to put a squiggly equals because I'm not sure, maybe like 37 or 38. I'm going to put a question mark because I just eyeballed that. The nice thing though is that you've got an equation right here. So we could actually plug in 35, since 35, x equals 35 corresponds to 2005, you could plug 35 in for x. So we could find f of 35. That's how we would write that using function notation. So f of 35 is 0.773. You could keep the 0 there if you wanted to. You don't have to though. Times 35. So I'm plugging in right here for x, plus 10.925. And if you go ahead and evaluate that with a calculator, I get 37.98, which is about 38. And you'll be given directions in terms of rounding when you do your homework, so don't worry about that. I should have put the directions on here, but you'll be told. So in this case, it would say round to the nearest whole number, and and that would be 38. So, and we're asked for percentages, so that would be about 38%. This next question, it says, about when did the percentage go above 25%? So we could look at the graph just to eyeball it. So we could look, the percentages is over here on the y-axis. We could look at 25%, which is right here, and go over to the graph. And then we could look down to see about what year that would be. To me, it looks like somewhere in between 15 and 20, so maybe like 17 or 18, which would correspond somewhere between 1980 and 1990. But let's use the formula. So if the percentage, this is the y, this is the dependent variable, so I'm going to plug that in for y. And instead of the function notation, I'll just replace f of x with y just to make it simpler. So I'm going to write this down. And I'm given 25%, I'm going to plug 25 in for y. Now, I can see in the past I've had students email me about this problem and say, I'm getting it wrong, and I look at their work, and what they've done is they put the 0.25, and they're doing they're converting their percentage correctly, and they're converting it to a decimal to plug it in. In this case, you don't need to do that though. And the reason you don't need to do that is if you look at the numbers that are on the graph for y, the percentages, none of those have decimals. So they just write the percentages as whole numbers. And so we're going to be consistent with that, and we're going to also write 25% as a whole number. So I'm just plugging 25 in for y, and then I'm going to write down the rest. And then I'm going to solve for x. So I plug in, whoops, not 95, that should be 925. I plug in 25 for y, and I'm going to solve for x. And so I'm going to subtract 10.925 from both sides. Okay, those cancel out, and then I end up getting 14.075 equals 0.773x. And then I'm going to divide both sides by 0.773. So 0.773 divided by self is just 1, so those cancel out. So I end up getting x equals this over here ends up working out if you use a calculator. Well, I'll just put squiggly. It's a long decimal here, so we get 18.2082, and it just keeps on going. Let's say in this case we're going to, especially with year, let's round to the nearest whole number. So I'm going to say 18. But then we want to actually find what year that is. So remember, 1970 is like 0. So what we could do is say 1970 plus 18, and we add those, and we end up getting 1988. So it's approximately 1988 would be the year where the percentage goes above 25. So this next part, we're still dealing with linear functions. We're going to talk about writing a function. So this example says a company has determined its price per unit is $73.50 divided by, so that gives you a clue that you're going to have to divide, by the product. So whenever you see the word product in math, think multiplication, of 0.05 and the number of units it sells. And so they want you to write the price per unit as a function of the number of units it sells. So P is price per unit, X is number of units sold. So let's just back up. So we're writing price per unit, which is P, as a function. So that's telling you you've got to start it like this, not x of x, which will never be the case, but we're going to write P of x. So P is price per unit, and we're going to find the price. Let's go back here. A company has determined its price per unit is, which is like equals, $73.50 divided by, so I'm going to write divided by, you can write it just like a fraction, the product of 0.05 and the number of units it sells, which we are told is x. So we're going to multiply 0.05 times x. Now, if you wanted to write it like this, when you see the divided sign, if you want to do divided by parentheses 0.05x, you can also write it like that. But it's more commonly seen as the first option. And then part B says use the model, which just means the equation you just made, to determine the price per unit if the company sells 3,000 units. So go back to where it says what's x and what's y to figure out, well, units, is that x or y? The number of units sold is x, So it's basically saying find P if X is 3,000. So it's telling you to plug 3,000 in for X. So we're going to do 7350 divided by 0.05 times 3,000. And you can use a calculator to evaluate that, and you end up getting 0.49, which is 49 cents. So the company gets 49 cents per unit if they sell 3,000 units. So that concludes 6.4. We're going to jump into 6.5 now, and we're going to talk about nonlinear functions. So functions when they're graphed that don't make lines. So we're going to start with quadratic, and then we'll end with exponential. So a quadratic function is a function that is commonly in the form ax squared plus bx plus c. That's not the only form that you can use for a quadratic function, but it's probably the most common one. The key here is that there's a term with an x squared. The x is optional. The number at the end is optional. So some examples might be f of x equals 3x squared, or f of x equals 3x squared plus 2. Or f of x equals 3x squared minus 5x plus 2. So you can have an x, you can have a number, but you don't have to. You have to have an x squared, and you can't have anything more. So you would not want to have like an x cubed. That would not make it quadratic. Quadratic functions are useful to model things that change directions and then increase and decrease, or decrease and increase, and we'll see, I'll show you that when we get to the story problem part. So when we deal with story problems, a lot of times it's helpful to solve quadratic equations, and if you were taking a algebra class, you would probably spend, quite a bit of time learning how to solve. If you have some experience with this, you might remember solving quadratics with factoring or using the quadratic formula, which is the options below. I'm going to go over those, but if these are completely new to you, I am going to encourage you to just use Desmos and look at the picture. So step 3 is look at the picture, and which just means look at the graph. And I'll show you how to do that as well. And it's totally fine to just look at the graph. So solving a quadratic equation means figuring out what x values you could plug in to make this equation true. And so one way to do this is you make sure that the equation is set equal to 0. And you solve by using the zero product rule and factoring. And so what you do is you try to factor x squared minus 2x plus 20. And factoring just means you're going to have two parentheses, and you can use FOIL, which means first, outer, inner, last. Again, if this means nothing to you, I would just skip this part, but I'm going to go through this in case this is a method that you prefer. So the way you could factor this would be x minus 10 and x minus 2. Because when you do that, if you multiply this out, you end up getting the original equation. So x times x, so first in the FOIL, is x squared, outer plus, minus 2x. Let me erase that so it's not confusing. So x squared minus 2x, inner minus 10x, last. Minus 10 times minus 2 is a positive 20. And if you simplify that, combine these two inner terms, you end up getting what we started with. So this is basically a simplified way, or another way to write this quadratic function. Then what we do is we use the zero product rule, which basically says if you have two quantities that are being multiplied with each other and the answer is 0, you know that if either of these are 0, it's going to make this true. So what you can do is you can set both of these equal to 0. So x minus 10 equals 0 and x minus 2 equals 0, and then solve. And if you solve these, you get x is 10 and x is 2. And those values, if you plugged either one of those in for x here or in the beginning, you would end up getting 0. So it would make this equation true. So those are the solutions. So x equals 10 and x equals 2. If you look at the picture, I'm going to actually jump to that next so that we can see a visual. So I'm going to just plug in the equation. So I'm going to plug in x. So I'm going to say x squared minus 12x plus 20 you end up getting a parabola. And the great thing about Desmos, they actually locate the solutions for you. The solutions are going to be the points where the parabola crosses the x-axis. So where the parabola crosses the x-axis. And it crosses at x equals 2, 0, and x equals 10. 10, 0. So if you plug in those numbers, you end up getting 0 for y, as you can see on the points. So that's a really quick way to solve these. So I would definitely use Desmos when you're doing your homework. So picture, you're going to look where the graph crosses the x-axis. And you're going to look at the x coordinates of those points. The y's will always be zeros. And then last, we could solve using the quadratic formula, which is this formula right here. And so basically all you need to do is you need to write down your function. I'll write it down again since we can't see it anymore. And then you're going to identify your a, b, and c. So remember, a is the number in front of x squared. So in this case, nothing is in front of x squared. So it's like there's an invisible 1 there. So I'm going to write a equals 1. B is the number in front of x. So b is negative 12. And c is the number added or subtracted at the end. So c equals 20. And then you're going to plug them into this formula. So I'm going to say x equals negative b, so negative 12, plus or minus the square root of b. Make sure you use parentheses when you square a negative, minus 4 times a times c, all over 2 times a. So then what we're going to do is we're going to simplify this further. So negative 12 is just 12, plus or minus. Negative 12 squared is 144, minus 4 times 20 is 80, divided by 2. And then I'm going to do it one step further. So 12 plus or minus the square root of 64 divided by 2. And then I get the square root of 64, and it doesn't always come out nice like this. Sometimes the square roots will be decimals, and that's okay. So if you're doing this method and you're thinking, oh man, I'm getting decimal, it doesn't mean that you're doing something wrong. So I get the square root, or not the square root, square root of 64 is 8. So you get 8 divided by 2. At this point, you want to evaluate this with the positive and negative. So you're going to say 12 plus 8 over 2 and 12 minus 8 over 2, and that's how you're going to get your two solutions. So you get 20 over 2 is 10, and 12 minus 8, 4 over 2 is 2. And so you get the same exact solution. So x equals 10, and then x equals 2. So you could graph it, quadratic formula, or factor. And this is going to come in handy when you have story problems in your homework and they ask, they might not explicitly ask to solve, but you are going to have to solve a couple times. So this next part, we're going to talk about graphing quadratic functions. When you graph a quadratic function, it's called a parabola. And a parabola is just a U shape. And the parabola could be facing up, we say, or it could be facing down. And whenever it's facing up, the leading coefficient, this is all written here, the leading coefficient is positive. So positive leading coefficient. And then if it's facing down, it has a negative leading coefficient. And the leading coefficient is the number in front of x squared. So whatever the, so for example, if you had a function negative 3x squared plus 2x, this is going to face down because the leading coefficient, negative 3, that's the number in front of x squared, is negative. If you had an equation like 6x squared plus 2, this is going to face up because the number in front of x squared is positive. So on your homework, that alone can help you narrow down your choices, since they're usually multiple choice for graphing, whether or not to try to match the graph with the equation. So you've got some options here in terms of graphing a parabola. I put two different options. I would definitely recommend probably the first one. The second one I think is great if that's familiar to you, then go ahead and use that one. But I would probably use the first one if it's in standard form, which means it looks like this. And then keep in mind you also have Desmos, so you can plug it into Desmos and just kind of double check that way too. So let's do the first example here. So this first example we have in standard form, and so the directions say first find, we're going to find the vertex. And this should say first find the x-coordinate, I'm going to say of the vertex. That's actually should be written in there. Oops, sorry, hang on a second, I got to get my pen back. Okay, so x-coordinate of the vertex. Oh, that's super thick. Let me change that. There we go. So in the way that you do that is you follow the formula. So I'm just going to write down vertex. The x value of the vertex is always negative b over 2a. So negative b, the b value is the one in front of the x. So remember ax squared plus bx plus c. So b in this case is negative 6. And the a in this case is going to be 1. Since it's like there's an invisible 1 there, so a is 1. So I'm going to plug those in. So I get negative 6 divided by 2 times 1. And so negative 6 is a positive 6 divided by 2. I end up getting 3. So that's step 1. Step 2 is to plug the x in to find y. So you're going to plug it into the formula. So the formula is x squared. So I'm going to plug 3 squared plus 6, not plus, it's going to be minus 6, minus 6 times 3 plus 5. And I'm going to evaluate that. So 3 squared is 9, and then I'm going to get minus 18, and then plus 5. And so 9 minus 18 is negative 9. Negative 9 plus 5 is a positive 4. And so we're going to write down our vertex, and we're going to write down our vertex is 3, comma, positive 4. So I'm going to go 1, 2, 3, 1, 2, 3, 4, and I'm going to plot it just like that. Okay, and then what I'm going to do is I'm going to try to find my other points. And you could also look at the leading coefficient, ask yourself, is it positive or negative? It's positive, so we know it's going to face up. And so at this point, so step 3 is going to be to find, so pick a few, so I would say 2 maybe, x values on either side of the vertex. And plug into the equation. So if the vertex is at 3, 4, so if I have a table of values, I know that if I plug in 3, I get 4. Pick an x value on either side. So maybe I pick 0. And actually, you don't even really need, you could even get away with just plugging in 1. So if I plug in 0, I get 0 squared minus 6 times 0 plus 5. And so negative 6 times 0, that's just 0. I end up getting 5. So 0, 5 is a point. 1, 2, 3, 4, 5. If you wanted to, you could just use symmetry to find the other side. So you know this parabola is going to face up. If from the vertex I went over 3, 1, 2, 3, up 1, you can do the same thing on the right side. But just to be sure, let's plug in 1, 2, 3, 4, 5, 6. Let's plug in 6 just to be sure. So 6 squared minus 6 times 6 plus 5. So 36 minus 36 plus 5, those cancel out. You end up getting 5, which is what we got with the symmetry. So that confirmed that we did that correctly. And then just remember, you do have the graphing software. So you can plug in here, we'll just go back, minus 6x plus 5, and you can see there, oh, I did something wrong. We've got a vertex of, let's see, did I put it in right? I did put it in right. Let's see, we should get a vertex of 3, negative 4. So let me go back. It's a really good, you're getting real-time learning here, real-time mistakes. So let's go back and see what we did, because we should have gotten a vertex of negative 4. So I'm just going to come back up here. Oh, you know what? I see my mistake right here. Negative 9 plus a positive 5 is going to be negative 4. And so that should be negative. So I'm going to go ahead and erase this. And I'm going to plot 1, 2, 3, 1, 2, 3, 4 down. And really my other work that I did should not be affected by that at all, because I plugged, I didn't deal with the vertex that I found in step 2. I really just plugged those x values into the equation. And so I get these points here. And then just to double check, and actually, you know what, that looks a little bit too much like a V. We want it to make it look like a U, even if it's a skinny U. Okay, that looks better. All right, so with our table, it should be 0, 5, 3, -4, and 6, 5. So let's go back to our graph on Desmos and see if we graph those points. So 3, -4, 0, 5, and then it's not located as a point, but we can see here that that looks like 6, 5. So that just confirms that what we did works. And again, I mean, great thing I checked it, because I wouldn't have caught my mistake otherwise. So hopefully that gives you a good idea of how you can graph. And then if there's a problem on the homework where the graph is in vertex form, then what you could do is you could, you have a couple of options. I don't have one of these examples on the notes, but you could multiply this out and write it in standard form. That might be the simplest, so you don't have to remember another way to graph. Or you could just go ahead and plug this into Desmos graphing calculator, and you could look at it that way, which I still think would be helpful and meaningful in terms of learning. Okay, so we talked about graphing. Let's do a story problem. So with quadratic story problems, we're going to do 2 of them actually, but there's a couple of common elements. A lot of times with quadratic problems, you'll have questions that ask you about the high point or the low point or the max or the min, and those are just clues that they're asking you to find the vertex, because, whoops, sorry about that. Whenever we have, gotta get my pen back, the vertex on the graph is always going to be the high or low point. So just keep that in mind. So this example says the percentage of population in the United States that was foreign born can be modeled by this function. X is the number of years after 1990, so that's important to note. And then P is the population. So when did the percentage, so that's like saying that's the Y variable, when did the percentage reach the low point? Now notice that the leading coefficient is positive, so that tells us that this graph is going to face up. And if this graph is facing up, the low point is just going to be the vertex. So one simple way to do this, you could use the equation on the previous page to find the vertex. That's one way. We could also plug this into Desmos and find the vertex that way, and I'm going to do that. So I'm just going to plug in, so 0.0033x, oh, let me go back. We're going to go y equals 0.0033x squared minus 0.420x plus 19.5. Okay, and so we see here we've got a graph. I'm going to zoom out. And it identifies the vertex right here. So it identifies this vertex at 63.636, and then it gives us a Y value. Now keep in mind, it's asking when. So it's asking for the date or the time. So if it's saying when, we're interested in the X here, because the X is the time, is the number of years. So you only have to write down the X value. So the X value of the vertex is 63.636. So I'm going to write that down, 63.636, and I'm going to round that to the closest integer, which is 64, and it's asking for the actual date. So if the X value is around 64, that would be years after 1900, so that would be 1964, so about 1964. And again, you could do the X equals negative B over 2A and plug in your B and A, and you would also get the same answer there. The next question is, what's the percentage in 2012? So this time you're given the year, you're given X and you're asked for Y. And so you could plug this into the equation. And so you could find, well, what is P of 2012? I don't want to write in 2012 though, because the years start at 1900. So you have to figure out how many years after 1900 is 2012. Well, from 1900 to 2000, that would be 100 years. And then we want 2012, so that'd be another 12 years. So total, we're looking at 112 years altogether. So, so X is going to be 112. So we want to find P of 112. So we're going to plug 112 in, and you can use a calculator for this. So 112 squared minus, and then when you evaluate that with a calculator, you get about 13.9. And so, and again, when you're doing your homework, you'll be given specific rounding rules for this. So the percentage was about 13.9% would be the answer. And then see if the model accurately predicts future trends. What will the percentage be in 2020? You do the exact same thing you did there. So going from 1900 again to 2000 is 100 years, and then we add another 20 to that, we get X equals 120. So basically they want you to find P is 120, and so you're going to plug 120 into the equation. So you're going to do just what you did above, only a 120. And when you plug that in, you should get about 16.6, which, not 9, I said 6, I wrote 9. 16.6, about 16.6 percentage there. So this next equation is a projectile motion problem, and let's talk about this for a minute. So in your homework, you'll get a problem like this, and you'll be given this projectile, if I can say it right, function equation, and let's talk about what it means. And so this V, we call this V sub 0 or V naught. This just stands for initial velocity, and then H sub 0 is initial height. So when you're reading the problem, I want you to think, okay, what's the initial velocity? What's the initial height? And you're going to have to plug those in to make the equation, because as is, there's too many variables. So let's read this bowling ball problem. So if a bowling ball is launched upward from the top of a 230-foot building, so you've got a building that's 230 feet tall. So from here to here, whoops, didn't mean to move that. Let me just move my screen back. There we go. Okay, so we've got a 230-foot building, and and now my pen changed. There we go. Okay, so we'll pretend like this is the ground and this is our building, and we've got a bowling ball at the top of this building, and it's launched upward, and then it's going to come down. So if it's launched with initial velocity, so there you go, we're told initial velocity, so that's your V sub 0 is equal to 60 feet per second. Find the maximum height. So on the picture, this kind of looks like a parabola. Imagine it goes down on the other side. The max height is just the vertex. So let's write down this equation. We've got initial velocity. Let's talk about initial height. If the ball is starting at 230 feet in the air, then the initial height is going to be 230. So my equation is going to be h of t equals negative 16t squared plus initial velocity 60t plus initial height of 230. That's your equation. Okay, so that's step one, is figuring out what the equation is. And then this confirms we've got a negative leading coefficient. It confirms that it's a facing down parabola, which is what this looks like. And so then if we want to find the vertex, there's two ways to do it. You could use the vertex formula. So step one is vertex formula. You could do x equals negative b over 2a, or you could graph it. I'm just going to graph it, because our focus here is really just interpreting this and not so much every single bit of the algebra. But I'm going to write y equals, instead of h of t, you're going to put y. because that's how Desmos likes this entered. So negative 16x squared plus 60x plus 230. So we've got a skinny parabola, and if we zoom out, you can see at the very top that tells us the vertex. So we look at the question, again, it's asking us for the maximum height and then how long it takes to reach the ground. Let's just talk about maximum height first. So if we're looking for maximum height, we've got an x and a y value of this vertex. 1.875 is the x, and then 286.25 is the y. In this case, our x-axis is time, because t is our independent variable. Our y is going to be the height. So our answer here, if we want to know the maximum height, is going to be the 286.25. That's the height. The time, 1.875, that's how many seconds it took to get to that max height. So 1.875, so I'm going to just minimize this. So if we were to do this formula, we would have gotten here 1.875, and then we would have to plug that in to find y. So really 2 steps in that process. But with the graph, we found that our vertex was 1.875 comma 286.25. So our answer for max height is 286.25 feet, and that gives us the answer. And then the second part of the question says, how long does it take to reach the ground? And so if it's reaching the ground, that means the height is going to be 0, which is actually your y. So y is the height. So if you wanted to know the time it takes to reach the ground, you could plug 0 in for y. So you could say 0 equals negative 16t squared plus 60t plus 230, and then solve for t. And you could use a quadratic formula. You could use factoring like we talked about before if it's able to be factored. It's not always. Or you could graph it. And so I'm just going to look at the graph since we've already done the graph and it's pulled up. And so we're looking at the time it takes to hit the ground. Well, there's 2 points here which would be solutions. One is where it starts. So well, I shouldn't say where it starts. If you look at this x value, it's negative 2.355. It doesn't make sense for us to represent time in a negative number. And so there are times where we use parabolas to model a situation, but not the entire parabola makes sense. And if you remember, like if the balloon is starting at the top of the building, we really are starting at time 0, which is up here. And so the left part of this parabola doesn't make any sense. It's not useful. So what we want to look for is this other solution right here. And if you want, let's see, we'll zoom in. Y is also 0 when x, or time, is 6.105. So at 6.105 seconds, the height of the ball was 0, meaning it reached the ground. So 6.105 is going to be our answer here. So time equals 6.105 seconds. And because this is a decimal, that tells me that factoring is probably not a wise way to solve this. So you could have used a quadratic formula here, would have been the best option if you want to solve it algebraically. And again, that negative time doesn't make sense. So we're not even going to write that down. Okay, so let's move on to exponential functions. Like quadratic functions, I'm not going to get into all of the details here, but just touch on the important parts so that you can learn to just quickly recognize, what is an exponential function, and then just very generally know, like, okay, does it increase, does it decrease? And so basically what we're going to start with is, let's just look at the form. So exponential functions are written in this form. So for example, you might have one f of x equals, c could be any number. So maybe it's, it could be 3 times, 2 to the, not fifth, to the x power. That's important. So the exponent here is always the x, the independent variable. Another example might be, you might not even have a c, or it might be 1. You might have one where maybe it's f of x equals 2/3 to the x power, where the base, we call it the number that the exponent is raising to, that number is less than 1, so it's a fraction. Whenever you have an a value, so the base, the number that's being raised to x, if that is greater than 1, that the function is going to be increasing. Okay, so it's exponential growth. So for example, like my example right here, that's going to be exponential growth. And so if the number is a fraction, if a is a fraction, then the number that's being raised to x, then it's going to be decay. And so it's going to go like this. And so this one is going to be growth. And so to graph, I think the simplest way to graph is just pick a couple values for x. 0 is always a good one to include. It's easy to plug them in for x to find y. And this is the same process we use for linear equations, and you can also do this for quadratic. So it's a great method because it applies to any type of function. So, and of course, we're going to use Desmos to check our work. So for this first one, I'm going to look at the a value, the number that's being raised to x. Since this is greater than 1, we know that it's going to be exponential growth. So the graph is going to look like this. This a value, so I'm just going to say a is greater than 1. This a value is less than 1. It's a fraction, so we know that it's going to be exponential decay. So that's just a good way for us to be able to identify. So if you're doing a multiple choice question, you could probably, knock off a few options just based on that. Next, I'm going to make a table of values. So I'm going to find a couple of x values to plug in. And I'm going to pick -1 and then 0 and then 1. So if I plug, and I'm plugging this into 2 to the x, so that's going to be my y point. So if I take -1, I'm going to say 2 to the negative first power, and you can use a calculator if you're not familiar with this, but basically what that means is it's 1 over 2 to the first power, or 1/2. So -1, 1/2 is a point. So -1 up 1/2 is a point. Now I'm going to plug 0. So 2 to the 0. Anything to the 0 power is 1. And again, you could use a calculator for this if you're not familiar with raising numbers to a 0 power. Just use a calculator to check your work. So 0, 1 is a point. So 0, 1 is a point. And then if we plug in 1, 2 to the first power is 2. So we get the point 1, 2. So now this doesn't give us a huge range here. If you weren't sure, you could plug in some other values, so like you could plug in 2, and if you plug in 2, you end up getting 4, so that would help. Or at this point, you could use the graphing calculator. You could use Desmos to double check your work there. And so if we're going to go with Desmos, we could just type in y equals and with Desmos, let me see here, you're going to want to, we've been choosing the a squared with quadratics, you're going to want to pick the a to the b because you want your exponent, the b represents the x here, so you're going to want to press that button. So for 2 to the x power, we're going to press 2 and then click this button up here, and it allows you to put an x in, and then this confirms that the graph that we just did looks correct. And so you can kind of just, I know it only explicitly gives you this 1 point, but you can just see here, just because it crosses at a nice intersection, that this is 1, 2, and this looks like -1, 1/2. So that confirms what we did was correct. And actually, while I'm here, I'll just go ahead and put in the next one. So 1/2, or you could do 1.5. It's really nicely formatted. And then click on the a to b button, raise to the x power, and then we get this exponential decay here. And so that's what your graph should look like. If you wanted to do it algebraically, then we could pick a couple of x values, so we could make our chart just like we did before, and maybe we'd pick, I don't know, maybe I'll pick -2 this time, and then 0, and then +2. So I'm plugging this into 1/2 to the x power. That's my function. So 1/2 to the -2 power means you're going to flip this and raise it to the second power. So it's like 2 squared or 4. So the and again, you can put this in your calculator, 1/2 raised to the -2 power, and you end up getting +4. So the point is -2,4. That corresponds with that, with what I just did there. So -2, 1, 2, 3, 4, +4. And then if I plug in 0, 1/2 to the 0 power, anything to the 0 power is 1, so I get the point 0, 1. Notice both of these functions had the point 0, 1. And then if I plug in 2, 1/2 to the 2nd power is just 1/2 times 1/2, or 1/4. So 2, and it's hard to graph 1/4, but you just try your best. And so we have a function that looks like this, which is exponential decay. And that's you know, a quick sketch of what we just saw from Desmos. All right, so hang in there. I know this is a long video. We have 2 more problems to do, and then we are done. So we've got, these are just story problems relating to exponential function. So this first one, Riverside County, California, is one of the fastest growing counties in the United States. One estimate uses this function, so I'm just going to write this down. So f of t equals a sub 0, 1.04 t to model the population, where a sub 0 is the population at time 0. So a sub 0, population at the time the model began, is what that means. And so in this case, it says the population in 2007 reached 2 million for the first time. So a sub 0 is going to be 2 million, because that's the initial population. And that's in, I'm just going to write 2007, so we remember when that was. So our equation, instead of a sub 0, I'm going to actually write 2 million times 1.04, and then that's to the t power. And so let's figure out what the question is. So it says, use the model to predict, usually that means plug and chug, or you can look at the graph, the population in 2027. So we have to figure out what we plug in for t. So t equals time. When t equals 0, that represented 2007. So if I'm interested in the time of 2027, we have to figure out how many years went by. Well, 20 years went by between 2007 and 2027, so t is going to equal 20. So that's really important. These problems sometimes can appear to be simple, which I suppose they are, but in some ways they're not, because if you even get the equation right, but you don't plug in, if you try to plug in 2027, you'll get an astronomically large number, because that's like 2027 years after 2007, which we don't want. So I'm going to plug in 20 for t. And so in your calculator, you're going to do this first. You could raise 1.04 to the 20th power, enter, multiply by 2 million, and you should get 4,382,246, and that's the amount of people in 2027. Okay, last problem. So we're going to talk about some investments. So we're just doing a review of compound interest, which we've done before. So if $10,000 is invested at 8%, so hopefully you remember from before, that's the initial principal. So I'm just going to put P equals 10,000. That's the initial amount of money that's invested. 8%. So remember that the rate is the decimal form of the percent. So 8%, we're going to move that decimal 2 spots to the left, is 0.08. So our rate is going to be 0.08. And then it's compounded quarterly. So quarter, think quarter, 4 quarters in a dollar. So quarterly means 4 times a year. So that means N is 4. Find the value. So the value, that's like find A of the investment after 40 years. So T equals 40. Remember that T is always in years. So if for some reason you get one of these where it gives you the months, you always want to convert to years. So I'm going to plug in everything I know. So I'm going to say A equals 10,000 times 1 plus 0.08 divided by 4 raised to the 4 times 40 power. If you have a TI 34 calculator or a TI 30, you can certainly put this in all at once if you want. I'm just going to show you how to do this step by step. And so I'm going to evaluate just this part in my calculator. I'm going to plug that in. I get 1.02. And then I'm going to evaluate just this. So 4 times 40, that's 160. Then you can go ahead and evaluate this. Raise 1.02 to the 160 power, and then multiply it by 10,000. When you do that, you get 237,699.07. So $237,699, or I'm sorry, $237,699.07, which is crazy because that person started with $10,000. So you can see how compound interest really, does a lot to grow your money. So thank you for hanging in there with me. This is the longest video of the course, I'm sure. There's a lot packed in there. Hopefully it was valuable. And as always, let me know if you have questions.